Okay, so before we start today, does anybody have any questions for me? Good. All right, so today we're going to do basically, it's not review, but just talk about things we've been already doing in slightly different language to tie some things together that maybe we've been already doing informally, but we should just be clear about what these things mean. And that's this, I've been doing this all the time. When I have two events, A and B, and I take the intersection of A and B, I keep calling that A and B. Which, you know, if you're doing logic, well, and A and B are propositions, then usually you write that as A with this pointy down thing B. So this is the thing that you usually read as AND. This is the thing that you read as intersection. And both make sense for what we're doing. All of our probability spaces are defined always in terms of this set of outcomes. And so, you know, events really are subsets of that set. So A and B are subsets. So it's true that you take their intersection. On the other hand, in natural, when we think of it in terms of natural language, there's a proposition which is the outcome came from the set A. There's a proposition which is that the outcome is in the set B. And when I say this, I'm really saying, yeah, the outcome came from the set A, and the outcome came from the set B. So this is a completely natural thing to do. And similarly, if I take the union of A and B, that's just A or B. The outcome came from the set A, or the outcome came from the set B, and we can think of it this way. Okay. Let me turn off the projector. Good. All right. So that's nothing exciting there. Nothing exciting. Just I've already been abusing this language, and I'd like to just make it clear that that's okay. So let's look at maybe a boring example to begin with. That's usually what we do. And then we work up to more interesting things. So for example, sometimes it makes more sense to think over in terms of this language. Sometimes it makes more sense over here. As long as we're doing things correctly, it's okay. But let's say that I look at this example, which is I roll or I toss a fair coin and roll an independent six-sided die. Okay, this is somehow the experiment that I'm trying to capture. And we can break that down sort of into two separate and independent experiments. So there's this experiment of tossing the coin, which has two possible outcomes, heads and tails. And each of those outcomes has probability 1/2. And there's this second experiment of rolling the die, which has 6 possible outcomes. And each of those outcomes occurs with probability 1/6. And if I say, well, I toss the coin and roll the die, then really, what are the set of outcomes? Well, it's the Cartesian product of these two spaces. So I take every outcome in the first one, heads and tails, and for each of those I make this many copies of it, 6 copies in this case, where heads, for example, is followed by 1, 2, 3, 4, 5, 6, and then tails is followed by 1, 2, 3, 4, 5, 6. So when I do this kind of experiment that proceeds in phases like this, where the phases are independent, then I can think of well, there's little individual experiments that happen at each step, and the whole experiment is just the Cartesian product of all those steps. Okay. So that's clear. All right. That's good. And, well, okay, so that's the space, but what are the probabilities associated with these things? So here I've somehow said that the coin and the die are independent. I actually haven't given you a definition of what it means for one experiment to be independent of another. We'll maybe mention that briefly. But for us, it means the following. If I take well, I mean, let's just think about it for a minute and say, well, just pick one thing in this set S, H 5. So the probability that I toss the coin and it comes up heads, and I roll the die and it comes up 5. So I've said that the coin and the die are independent. So that should mean that this is the probability of H times the probability of 5, right? So independence means, right, so the event really here is I tossed the coin, it came up heads, and I rolled the die and it came up 5. So if the coin and the die are independent, that means the probability of these two events is the product of their probabilities. But what's this probability of H? Well, actually, that's in this space here. So let's call this probability function the C1, and let's call this one the D1. So this is in the first one, and this is in the second one. And indeed, so the probability of heads in the first space is 1/2, and the probability of 5 in the second space is 1/6. So we get 1/12. Okay. And actually, when I say that two experiments are independent, that's really what I'm using as my working definition. If I take an outcome from the first experiment and an outcome from the second experiment, then the probability that the first experiment did this and the second experiment did this will be just the product of those two probabilities. So the probability function over this set S, which is the whole experiment, we get it from these two things here, and the fact that we're assuming that these are independent. And notice there's nothing special about H here, and there's nothing special about 5 here. So no matter what we put here, we're going to get the 1/12. So the probability of omega is 1/12 for any omega in S. Okay. So here we get a uniform probability space over these pairs. That's all easy. All right. Now this becomes handy. So let's say, take two events. Say A is the event, the coin comes up heads. And B is the event, the die comes up with an even number. So in this simple experiment of just tossing the coin, that's a very simple set. It's a set with one element. And in the simple experiment of just rolling the die, that's a set with 3 elements. And now, in the combined experiment, we can ask, well, what's the probability of A and B, right? So, and I'll write it this way. So that should be the probability of A times the probability of B. So what's the probability of A? So I toss a coin and it comes up heads. That's 1/2. And what's the probability of B? So 3 elements here, and the size of the set is 6, so that's 3/6, which is also 1/2. So we get 1/4. Or I could have done it the really long way and worked in the global space, in this combined space, but then things get longer, because in that space, A looks like this. And B looks like, we can explicitly compute it now, it looks like heads 2, heads 4, heads 6. So the probability of A and B will be 3/12, which is also 1/4. So there's sort of an easy way to do it over here on the left, and then there's the long way to do it over here on the right. But you get, as you should, the same answer either way. And very often, as soon as you start working on bigger, more complicated things, you always do it the easy way here. And that's just because the space here of possible outcomes, the more steps you have, the bigger and bigger it gets, right? Even if there's only 2 outcomes, even if all you're talking about is tossing a coin n times, then the size of the outcome set is 2 to the n. And that becomes very big, and certainly explicitly writing out all of the events like this just can become too much. So it's a lot easier than to work with this kind of thing. And so that's where what we'll do more and more for the next little while. Okay. Questions? All right, good. So let me write down a lemma that is not in the book, although it's used everywhere. So I'll just write it down. So here it is. Let A1, A2, A3, up to AN be a set of mutually independent events, then 2 things are true. One of them is obvious, because it's actually the definition of mutual independence. It's in the definition of mutual independence. And the probability of A1 and A2 and A3 and so on all the way up to AN, that's just the product of those probabilities. So this first thing shouldn't be a surprise, right? Because the definition of mutual independence that we saw last class says that if I take any subset of the events and ask what's the probability that they all occur, then that is just the product of the probabilities of their individual occurrences. So that's just right there in the definition of mutually independent. In particular, in this case, I take the whole subset, so the subset consisting of everything. More useful and confusing is this one. If I take A1 or A2 or, and so on, or all the way up to AN. So that, what's the probability that A1 occurs, or A2 occurs, or A3 occurs? That's 1 minus the probability of A1 times 1 minus the probability of A2 times 1 minus the probability of AN. Okay, this one is a bit less obvious. It's actually, well, we'll prove it in a second, but we're basically using two applications of the complement rule, or if you like, De Morgan's law. But if we think about what this means, what's the probability that A1 or A2 or A3 or A whatever occurs? Well, that's the probability that at least one of them occurs. And we've seen when you ask questions like, what's the probability that at least one of these things is true, it's usually easier to compute the probability that none of them is true. So that's what's happening here. What's the probability that none of these occur? That's what we're going to do over here. And then we take 1 minus that to get the probability that at least one of them occurs. Okay. So there's no need to prove A, but if you want to prove B, just do this. The probability of A1 union A2 union AN. So this is a set, and it comes from some universe which we've been calling S all the time. So, and its union is also a subset of that universe. So I can take the complement of that set. So I can take the complement of that set, and I can take the complement of that. So if I take the complement of a set, and then I take the complement again, it's the same set, right? So start with A, look at what's outside of A, and then look at what's outside of that. Well, that's only the stuff that's in A. So that doesn't do anything. But we have seen already that to do the complement of an event, we know how to do that. So I take 1 minus the probability of A1 union A2 union AN. So take away one of those complements and I get this. So that for any event A, the probability of not A is just 1 minus the probability of A. So that's all you use here. And now you use De Morgan's theorem, which is, or De Morgan's law, I think it's called. When you have the complement of the union of things, that's the complements of the individual things, the intersections of the individual complements. All right. Well, we're almost done. We saw that, okay, A1, A2, and so on, AN, the thing says that these are mutually independent. And we saw that if events are independent, then their complements are also independent, which means that we can do this thing here. This is not A1 and not A2 and not A3 and so on. Well, that's just the product of their probabilities. Not AN. And then we're done, right? Because the probability of not A1, that's 1 minus the probability of A1. The probability of not A2, that's 1 minus the probability of A2. And so on. Probability of not AN is 1 minus the probability of AN. This is a really common and useful thing to end up doing with independent events. You'll do this a few times, and you should get comfortable with it and not forget any of these steps of complementing and then taking 1 minus a probability. So notice it happens on 2 layers here. To get rid of the outer complement, we did this, and then to get rid of all the inner complements that pop up, we had to do it inside each one. Sometimes when you're doing these things quickly, it's easy to forget one of those things and get a strange looking answer. So let's look at another probability space, actually one that I mentioned. So the space is, or the experiment is, we toss a coin, a fair coin, comes up heads or tails, n times. And let's say for each I in 1 through n, we define the event Ci, which is the ith coin came up heads. And we can ask, about a couple of events. So let's look at event A, which is all the coins came up heads. Well, if all the coins came up heads, that means that the first coin came up heads, and the second coin came up heads, and the third coin came up heads, and so on. So then, what is the probability of A? Well, it's just the probability of this, C1 and C2 and C3, Cn. And these coins are, coin tosses, we sort of always think that one coin toss does not affect the outcome of another one, so these are independent, they're mutually independent, and so, well, then we can use the first part of that lemma up there to say that that's just the probability of C1 times the probability of the C2, and so on, times the probability of Cn. And this is a half times a half times a half, and so on. So it's 1 over 2 to the n. So as n gets big, it becomes very unlikely that we're going to get all of those coin tosses coming up heads. It happens if n is 10, then it's only 1 out of 1,024. The probability is only 1 out of 1,024. Okay, good. So then let's look at event B, which is the probability that, or the event that at least one coin came up heads, which is actually the first coin could come up heads, or the second coin could come up heads, or the third coin could come up heads, or any one of them. Even the nth coin could be the one that came up heads. So that's what the event B looks like. The first one came up heads, or the second one came up heads, or the third one came up heads. So, and now we can use this thing that tells us what the probability of the union of all these mutually independent events is. So we get a big leading 1 minus the probability of not C1 times the probability of, or if you like, let's do it more carefully, 1 minus the probability of C1 times 1 minus the probability of C2, so on, all the way up to 1 minus the probability of Cn. And the probability of C1, probability that the first coin comes up heads, is 1/2. So the probability that it doesn't come up heads, or 1 minus that probability, is also 1/2. And the same thing, this is also 1/2, this is also 1/2, so on. So we get 1 minus 1 over 2 to the n. So there's a really baby example of how to use that lemma to answer these two questions. So the probability that they all come up heads, that's very small, looks like 1 over 2 to the n. The probability that at least one comes up heads is actually very close to 1, right? This is 1 minus something that's getting smaller and smaller. Now, you're probably looking at this and thinking, well, I could have done that a lot more easily, because if at least one comes up, if you're just using directly the complement rule, the complement of this is they all came up tails, which is 1 over 2 to the n, and 1 minus that. But we'll see that, not everything is so perfectly symmetric like that. And that lemma over there gives you the general rule that you should apply. Okay? So let's look at a really computer sciencey application, or maybe it's an electrical engineering application, I don't know. But I don't know if you guys, some of you may or may not know this, but most of you have bought a computer before, and part of that computer is the microprocessor that's on it. So this i5 or i7 or i whatever, and those processors differ in like the number of cores on them and things like that. But you may or may not know that in some cases the 4-core processor and the 2-core processor and the 8-core processor are actually made by the same process. So Intel makes these things, and of course the tolerances are really small, right? They're talking about nanometers as are the tolerances of these things, and so it can easily happen that in the fabrication of this thing, something doesn't work, something fails, and the thing comes out and it doesn't work. But they make one of these things that actually has whatever, 8 cores on it. And after it's made, they come out and they test them. And they say, okay, well, okay, I tested this one, and these 4 didn't work, but that's still okay. We can still ship this as a 4-core processor. So even though the thing is half broken, those are disabled, and the actual input gets done on, the actual work gets done on these 4. Or maybe 5 of them broke. That's okay. We can still ship this as a 2-core processor. So this is something that really happens. I mean, the processor that's in your laptop is probably not fully functional. It didn't come out perfect from the factory. They just disabled the parts of it that don't work properly. So let's look then at something related to that. And actually, this appears all the time in the internals of these things. So we're going to look at circuits and sequential versus parallel circuits. So here's what a sequential circuit looks like. There's an input. So you imagine them as wires, but of course they're sub-microscopic, so you don't actually see the wires. And then there's a little processing that gets done to that input on some circuit, let's say circuit 1. And the output of that is fed into some other circuit, circuit 2. And the output of that is fed into circuit 3. And so on. And eventually that's fed into circuit N. And circuit N gives you the final output. All right. So let's say, suppose well, let's do it this way. Let Ci be the event. The ith circuit doesn't work. We usually say that the ith circuit fails. Okay, so these things go through this manufacturing process, and each one of them has some chance of failing, and we'll just assume that the probability of Ci is just some number p, I don't know, between 0 and 1. Depends on how good the manufacturing process is. The better the manufacturing process, the closer p is to 0, and the worse it is, then the closer it is to 1. All right, so, and we'll also assume, again, assume that the events C1 or Cn are mutually independent. And now we'll take A to be the event. The whole circuit works. All right, so if this is what the circuit looks like, if the whole thing works, what has to happen? This has to work. This has to work. This has to work. All of these things have to work. Okay? So the whole circuit works means that C1 does not fail. So C1 works. And C2 also works. And C3 also works. And so on, all the way up to Cn. Okay. Well, now we know the probability of A, right? Everything is mutually independent, so the probability of A is just the probability of all of those things happening. We've just said that Ci, the probability of Ci is P, so the probability of not Ci, which is what we have here, is 1 minus P. So we get 1 minus P, and that's for all of these things. So we get 1 minus P to the n. So the moral of the story here, in particular, if you take P is equal to a half, for example, is that sequential circuits are not very reliable. They need everything to work correctly in order for them to work. Because if the circuit is faulty with probability a half, then each individual circuit with probability a half, then the entire thing is only works correctly with probability 1/2 to the n. Okay. So not a good way to do things. And intuitively, we know this, right? Even forgetting about working with circuits, but just think of if you have a job to do and you have n people to do it, and you say, okay, the way it works is you do the first part, and then you do the second part, and you do the third part, and so on. Well, if you have a lot of people, it becomes more and more likely that at least one of them is not going to do the thing that they need to do, or not do it correctly, which means it's more and more likely that this is just not a good strategy to get things done. Okay. So it sounds good because in this case, I mean, let's say, it sounds good because it distributes the work so nobody has to do a lot of work, but if one person drops the ball, then it's over. So the alternative to a sequential circuit is a parallel circuit. And a parallel circuit looks like this. There's an input. It immediately gets split off. Into separate things. And so each of these is a whatever processor or a circuit that does the computation that it's supposed to do. They're all doing the same computation, or they're all trying to do the same computation. And then the outputs are, let's make it really simple, combined in such a way that, well, as long as one of them works, then we'll get the correct output over here. All right, then we stick with the same setting. Ci is the event the ith circuit doesn't work. And let's let B, so this is the whole sequential circuit. Over here, we'll take B to be the event that the parallel circuit works. Which happens, the parallel circuit works as long as C1 works, or C2 works, or C3 works, or and so on, Cn works. Right? As long as one of these things works, we'll get the right answer here. And so now we can use that rule again. It's over here, so there's a big leading 1 minus those probabilities. The probability that this one works is 1 minus p. The probability that this one works is 1 minus p. The probability that this one works is 1 minus p. the probability that, let's be even more careful. The probability that this one works, well, actually we're really good here. The probability that it works is 1 minus p. The probability that so the complement of that, 1 minus that, is actually just p. So here, and so that just gives me p to the, okay. Yep.
Probability of C equals P, so probability of not C equals 1 minus, no?
So here, the event CI is the circuit doesn't work.
So probability that it works will be 1 minus P.
So the probability that it works will be 1 minus p, and that's what we have, but then this formula says it should be 1 minus that thing. So think of it quickly. When does this fail? When does the whole thing fail? It fails when every single one fails, right? So each one fails with probability p. So this is the probability that every single one of those n things fails, and as long as that doesn't happen, we succeed. Okay. Okay. So already you see, keeping track of these 1 minuses takes some effort. So it's easy to forget to do a 1 minus here and get a weird looking answer. And here again, we can check this. Here we said if you take p as a half, then this is 1/2 to the n, so not very good. And here if I take p as a half, this is 1 minus 1/2 to the n, so very close to 1 as n gets bigger. And so really what the processor manufacturers are doing is they're doing this a slightly more, their version of this is if I want to sell a 1-core processor, then I make an n-core processor, and as long as one of them works, I can ship the thing to a customer. And actually, maybe there's some nice exercises you can do with, well, what if I make a n-core processor and I want to sell an n over 2 core processor? What's the probability that this thing will work or not? Okay. All right. Any questions? So that was all the boring stuff. Now we're going to do something cool. Something that is actually really relevant because it's used all the time, and something that on the face of it looks like you wouldn't. It's one of these problems, again, that you think, oh, maybe there's no solution, at least the first time you see it, and then the solution ends up being absolutely beautiful. So in the book, this is described as choosing a random element from a linked list, which is not such a compelling application because there's a couple of easy ways to do that without being intelligent at all. But here's another way to think of it. So we have a stream D1, D2, D3, D4, up to Dn. So what is a stream? A stream is stuff that's arriving. So, and these are data items. So for example, if you're Amazon, this stream could be click events that are happening as users are using your different parts of the website that they click on. Those things all come in some stream and in some order. So they show up like that. And I don't know, we want to do we're trying to collect statistics, and for us what we need is a random item from this stream. So we want to choose a uniformly random item in this stream. So what does that mean? That means that for each I in 1 through n, we want to set up some experiment where the probability that we choose di is equal to 1 over n. So we want a uniformly random sample. All right. And this is we use the word stream here. It usually means there's a lot of it, and it also means it's arriving, and once it's gone past, you don't get to go back and look at it again. So unless you want to save it, right? These are users using your website, for example. Unless I want to save every single thing that every single user in the world does on my website, then once this event happens, I get to look at it, and then it's gone forever. Right? I don't get to recreate it. So unlike a linked list, I can't just go back to the beginning of it and scan it again. Okay, so this is what I want to do. And you think, okay, well, this is easy. So here's an algorithm for that. Let's say I is equal to 1. And let's say R is a random integer. So this is random integer in 1 up to n. And then you say, well, the stream is not empty. Then we'll say D gets the next item on the stream. Well, I've already picked a random integer between 1 and n. So I'll say if I is equal to R, then the item that I'm going to give you, the sample item, is just going to be D. And then no matter what, I equals I plus 1. And then finally, once that's done, we return S. Okay? That looks easy, right? And it is easy. So I have this stream of n items coming in. I don't know what they are yet, but if there's n of them, I'll just pick a random integer between 1 and n. I'll read the stream one element at a time, and keeping track of the index of this one. So first time through this loop, I is equal to 1. The second time through this loop, it's equal to 2. Third time, it's equal to 3, and so on. And eventually, at some point, that iteration is going to be iteration R, in which case I grab that data item, save it, and return it at the end. So nice thing about this is we don't need a ton of memory for this. We just pluck things off, watch things go by on the stream, and we grab the one we want and save it. So that looks easy. Here's the problem. Or here's what makes this interesting. Well, this is a data stream, and it's generated by users, and things happening? Well, we don't know the value of n. So we don't know in advance how many people are going to click on our website today. At the beginning of the day, let's say this is the data of all user clicks in the 24-hour period starting at midnight. I don't know how many that's going to be tomorrow. At midnight, I don't know how many it's even going to be by the end of the day. So already the first sort of step in this algorithm is a problem, because I'm supposed to pick a random integer that's between 1 and the number of events, or number of data items, and I don't know the number of data items. Okay. So what can we do? Any other suggestions? I mean, let's say someone says, you've got to solve this. You got to do it. Just what would you do? Well, one thing you could do is just buy a big hard disk and say, well, what I'm going to do actually is, as the data comes in, I'll just save it all. So get this while loop, but instead of just forgetting about this thing at each step, you save it somewhere. At the end of this loop, you know the value of n. You pick this random value of n. You pick a random integer between 1 and n, and then you go on your hard disk and you grab that thing that's stored at that location. That also works. Problem is, you need a big hard disk for it to work. And depending on the application, that just may not be feasible. So you may not be able to buy a hard disk that big. And this is especially true for for the sort of, if you think of this from a commercial point of view, yeah, you're a startup company and you start up some web service or whatever, and you have exactly this problem to deal with. So you buy an 8 terabyte hard disk, and that works fine because when you start up, you have like 50 customers or something. But then you become Facebook, and you have whatever, 6 billion customers. And now that just doesn't work for you anymore. So that initial solution of trying to save all the data doesn't work. So can we come up with something that's going to work forever? And the answer is yes. And here's what it looks like. So this is not an option. We don't get to choose a random data item. But otherwise, the thing is going to look like this. It's going to scan through the whole stream. At each step, it's going to look at this data item, make a decision, and maybe save it. And at the end, it's going to return whatever is saved. Just the only difference is, how does this decision get made? And how this decision gets made is you pick, at the ith step, you pick a random integer from the set 1 through I. And if you happen to pick a 1, then you save that data item. Okay. So if you think about this, unlike in the previous version of this thing, this line might get executed more than once, right? Can it get executed 0 times? So is there any value of I for which you're certain that it gets executed? So when I equals 1, which is what we start with, if I pick a random integer between 1 and 1, I get 1, and that's equal to 1. So definitely I'll save that first data item here. Okay. So it'll never happen that the value of s is undefined at the end of this thing, unless the stream itself is empty, in which case we have these data items, x, y, and z, and initially we take s equals x, and then for y, that's the second iteration through the loop, we toss a coin, right? So we pick a random number between random integer, 1 in the range 1 to 2, so it's 1 or 2, and if it happens to be 1, then we'll take y, otherwise we'll stick with x. And then the third time through the loop, we pick a random integer between 1 and 3, and if it happens to be 1, then we'll take z, and otherwise we'll keep whatever we currently have. So is it clear how this works, if not why it works? All right. So what we're trying to guarantee here is that the probability that we choose di, for any particular I, is 1 over n. All right. Well, we can check one of those things very easily. So remember, our data stream is d1, d2, d3, up to dn. So that means with probability 1 over n, we should return dn. Does this algorithm do that? Well, when do we see dn? We see dn at the last iteration of this thing. At the last iteration, the value of I is n. So we're choosing a random integer from 1 up to n. And if it happens to be equal to 1, which happens with probability 1 over n, then we save that thing, and then the loop is over, it's done, and we return it. Okay. So one thing we know, we've already can just deduce by looking at this, the probability that we return dn, that's 1 over n. Okay. Well, that's just one value of I, the case I equals n. We need to check this for all possible values of I. So, well, let's look at D2. What can you tell me about D2? So, what's the probability that I'll even save D2 when I see it? Okay. So with probability 1/2, I'll save D2. So it'll be there. But then, to return it, then I should never save any of these other things, because this next thing I save is going to overwrite D2. Okay, so D2 somehow, yeah, it's more likely that I'll save it 1/2, which is bigger than 1 over n in general, but it's also much more likely that I'll throw it out. So I need to figure out really what is this probability that everything goes right for me, for example, and everything goes right for D2 means I save D2, that happens with probability 1/2, and then I don't save D3, I don't save D4, I don't save D5, I don't save D6, and so on. Yep. We're not going to prove it by induction. You might be able to. To prove it by induction, ultimately we'll prove it using a telescoping series, which telescoping series you can always prove things about them by induction. But I think it'll be a bit easier if we see the whole thing that happens. So now let's fix what are the what's the randomness in this algorithm? Well, the randomness happens here. We may keep making these choices. So let's define the sort of basic, and these are independent choices. Each time we ask this thing for a random number, we get a different one that's not related to any of the ones before it or any of the ones after it. So, let's do what this whole lecture has kind of been leading up to, which is we have this huge space of ways that this algorithm could execute. In fact, there's 2 to the n ways the algorithm could execute. It's not even a uniform space because we keep changing this probability here. So let's deal with that. Let's break it down into just the individual pieces. So I will say Ci, this is for each I in 1 to n. Ci is going to be the event. I save. We save data item di. Okay? And that means that this line executes here. All right? So, what is the probability of Ci? What's the probability that this line executes for the ith data item? 1 over I. It's the way we designed the thing. All right? So that's true for each I in 1 through n. So now let's look at the following, which is the event, let's call it EI, which is the algorithm returns the data item di. So if this thing returns the data item di, well, that means it had to save data item di, right? If it lets it go by without catching it, it's definitely not going to return it. And it should not have saved data item I plus 1. And it should not have saved data item I plus 2. And it should not have saved data item n minus 1. And it should not have saved data item n. That's exactly the way this is the only way that this thing can return di as an output is if it saves it and then it doesn't save anything that comes after it. That's clear? All right. And what we need to show is that the probability of EI is 1 over n. That's what we're trying to show. So let's just compute it and hope everything works. All right. So these events, Ci, Ci plus 1, Ci plus 2, and so on, they're mutually independent. So the probability that they all occur, or in fact, Ci, not Ci plus 1, not Ci plus 2, and so on, all the way up to not Cn, those are mutually independent. So the probability that all of them occur is just the product of their individual probabilities. So that's the probability of Ci times the probability of not Ci plus 1 times the probability of not Ci plus 2, and so on, all the way up to the probability of not Cn minus 1 times the probability of not Cn. All right. So let's write those in. What's the probability of Ci? It's written right there, 1 over I. What's the probability of not Ci plus 1? Well, it should just be 1 minus 1 over I plus 1. That means this one is 1 minus 1 over I plus 2. This one is 1 minus 1 over n minus 1. And this one is 1 minus 1 over n. Okay, good. So we've got 1 over I. And I want to write this in some more convenient way. So this is something divided by I plus 1. Right? It's the denominator here of I plus 1. So it's something divided by I plus 1. What is that something? It's I. Right? Because I plus 1 over I plus 1 is 1. But we don't have 1, we have 1 minus 1 over I plus 1. So this is just I over I plus 1, right? What about this one? This is something divided by I plus 2. What is that something? I plus 1. Let's do one more. The next one in the series, which we don't see up here, is something divided by I plus 3. What's that something? I plus 2. And this goes on right up to here. This is something divided by n minus 1. And we see the pattern now. The number on top is always 1 less than the number below. So if I have n minus 1 below, n minus 2 on top, and then finally I finish with n on the bottom and n minus 1 on top. Okay, this is the crucial step. So everybody sees what happens there? Not terribly complicated. It was just us writing this as a single fraction with a common denominator. All right, so what do I see here? Here's an I in the denominator, and here's an I on top. What happens to those? They cancel out. All right, here's an I, so in the end, I don't want anything that has any i's in it or anything. I want 1 over n. So let's see if we can get rid of everything other than the 1 in the n. Here's an I plus 1 on the bottom. Here's an I plus 1 on top. Those cancel each other. Here's an I plus 2 on the bottom. Here's an I plus 2 on top. Those cancel each other. Here's an I plus 3 on the bottom. And if there was another term here, I would see that I plus 3 on top. And so in the end, the one just before this canceled out the n minus 2. Here's the n minus 1 on the bottom. Here's the n minus 1 on top. So I just showed that the probability that I return the data item di is 1 over n. And that's true for every value of I in 1 through n. So that means this thing does exactly what it's supposed to do. It's equally likely to return each of those data items, each one with probability 1 over n. It does that without knowing the value of n in advance. and without storing anything more than one data item at a time. It's a beautiful result, and really relevant in today's age of what they call big data. All right. Any questions? Yeah?
So, if you consider the case where we only marking like the meaning of this certain, this probability of 1 over the probability of 1.
Yeah. So if n equals 1, meaning this was a very slow day in your e-commerce store and you only had one customer click, then you take the sample that you get is exactly that one item. Right? That's still, if n equals 1, then there's only d1, and you should return d1 with probability of 1 over 1, which is exactly what you do. If you only had 2 customers that day, then
So
with,
each one has probability of 0.
yeah. And the nice thing about this is you can stop at any time and know that whatever is currently here in S is equally likely to be any of the things you've seen so far. So maybe it's not that the data stream runs out, it's just that you decide to look at it now. And you'll know that you have this guarantee that whatever is in S here is equally likely to be any of the things that came before. Okay. So that's a good place to leave it for today.